Today I'll be presenting to you with my colleague Yijian Huang our work on TopOpt.jl, which is a topology optimization package written in the Julia programming language. So before we start, just a short introduction about ourselves. So I am the creator of TopOpt.jl. I started TopOpt.jl almost 3 years ago when I first started my PhD. Currently, I'm a final year PhD student at University of New South Wales, Canberra. I'm also a scientist at Puma's AI, which is a pharmaceutical modeling and simulation company. I regularly contribute and mentor at a whole bunch of open source projects. And you can reach me on this email, and this is my GitHub handle.
Hi, my name is Yijiang Huang. I'm a contributor of TopOpt.jl. I'm currently a third-year PhD student at MIT's Building Technology program. My main research is on robotic fabrication and assembly of spatial structures, but I have a strong interest in topology optimization. And I've been working with Mohammed on TopOpt.jl for almost a year now. We're thrilled to be here today to present you the latest features and advancement of this exciting software package.
So before we start talking about TopOpt, TopOpt.jl is a topology optimization package in the Julia programming language. So let's first talk about the Julia programming language. So Julia is this fast but dynamic and interactive language, a programming language. And perhaps this is a relatively odd statement to hear because most fast languages tend to be statically compiled like C or C++ or Fortran. And most dynamic languages tend to be natively slow, like Python or R or MATLAB. But Julia somehow manages to combine both of them. And it does this using a concept called multiple dispatch, which basically allows, enables the dynamism of the semantics. But sometimes the dynamic behavior can also be equivalent to static behavior, which the compiler can figure out and then use this to optimize your code. However, the semantics of your code remain to be dynamic. And so multiple dispatch basically is this concept, which you can read more about. It's not object-oriented programming, but it allows method selections. If you call a function with a whole bunch of arguments, the method selected depends on the argument's dynamic type or value type. And this is actually particularly powerful, and more details, like the Stefan Karpinski goes into more details into this, why multiple dispatch is so effective in practice. In his talk, The Unreasonable Effectiveness of Multiple Dispatch on YouTube. So I definitely recommend you go and take a look at that. So beside the design of the Julia programming language, which makes it dynamic and fast, Julia actually has a really great package manager that just works on all operating systems, so Windows, Linux, and Mac. We have great cross-language interoperability. You can call functions or packages from pretty much all the famous programming languages you can think of. And one of my personal favorite features is Unicode support. So you can write, like using Greek letters for your math symbols, like rho and sigma and so on. So in TopOpt.jl, we have this workflow that you define your problem first, which involves defining your ground mesh, the geometric and field interpolation functions, perhaps the material properties like the Young's modulus or Poisson ratio, the loads, the boundary conditions, the ground mesh could be 2D or 3D, could be truss or continuum mechanics based, like quadrilateral elements and hexahedral and tetrahedral and so on. Once you have your problem definition, now you can define a finite element solver. And what this does is it takes care of the assembly for you, the linear system solve or nonlinear in the future, but we currently only support linear systems. It takes in the Roman, which is the minimum pseudodensity. Your pseudodensity is the penalty. The linear system solver can be either a direct solver based on Cholesky decomposition, or it can be an iterative solver using like the conjugate gradient method, for example. All of these iterative methods can be either use the matrix, like the stiffness matrix, so it requires assembly of the global stiffness matrix, or some of them can also be matrix free. And some of those methods can also be either on the CPU or on the GPU. Once you have your finite element solver, now you can go ahead and define your functions like compliance, your stress, your displacement, and so on. So some of these functions require a finite element solve, and some of these functions do not require a finite element solve, like the volume or the Heaviside projection, for example. And in TopOpt.jl, these functions naturally compose, so you can define some functions and then stack them on top of each other. on top of some regular Julia functions, not even defined as part of TopOpt.jl. And once you define your objective and constraints and all the functions that you need, you can go ahead and define your optimization problem or do your optimization. So this involves defining your model, specifying some variable bounds, maybe inequality constraints, some equality constraints, perhaps integer constraints if you want some variables to be integers. And in the future, we also plan to support semi-definite constraints. Then you do your optimization and you visualize, post-process, and repeat if necessary. So as you can see, there is a clear separation between the function definition, and which sometimes uses a finite element solver, and the optimization. And the way this is actually enabled is using a concept called differentiable programming and automatic differentiation. So Julia as a language actually prides itself as being a differentiable programming language. So almost the whole language is differentiable. You can actually write arbitrary Julia code and just ask for the gradient of the function or the Jacobian or the Hessian, and you can get the gradient or Jacobian or Hessian without doing anything extra. This is especially powerful because it enables you to not worry too much about deriving gradients manually, which a lot of people painfully have to do, especially in topology optimization. And so a lot of these functions, whether it's scalar functions, matrix functions, linear algebra functions, they are all differentiable. They're all compatible with the automatic differentiation tool. And sometimes you, for example, may define a function, but you know the analytic gradient, so maybe you don't want to let the automatic differentiation automatically differentiate it. So you can also specify analytic gradients for some functions, and you do this by treating this function like a primitive. And the automatic differentiation tool or package will basically combine all the primitives together to build up the gradient function automatically for your more complicated function that's composed of a whole bunch of primitives. And so you can rely on automatic differentiation, or for efficiency, if you want, you can also define analytic gradients and compose them with other analytic gradients or analytic adjoint rules for other functions. And so automatic differentiation for topology optimization, the way I see it is that it's probably going to be a significant part of topology optimization in the next decade or so. So currently, actually, the state of topology optimization is very, very similar to the state of deep learning and neural networks a few decades ago, where in topology optimization, we often have hierarchical functions of physics-based and regular mathematical functions, like think of the checkerboard filter, the Heaviside function. None of this is physics-based, but then you have you need to assemble the stiffness matrix and then do the like find displacements and then find compliance and so on. And so you have hierarchical functions, functions of hierarchical nature. And in deep learning, we also have hierarchical functions or functions of hierarchical nature, where each primitive function is known as a layer. And the layer often involves running some complex tensor operations, which different types of layers have different types of or run different types of tensor operations. In topology optimization, different functions run different types of physics simulations, or sometimes just basic arithmetic, like linear algebra or even tensor operations. And so there's also a lot of similarity here. And many years ago, a lot of effort was actually committed to driving gradients manually of loss functions in machine learning. But nowadays, everyone basically uses automatic differentiation, or most people use automatic differentiation, whereas in topology optimization, unfortunately, we still have to actually derive or manually derive gradients and Jacobians of functions. And a lot of papers just like sadly still manually spend maybe half the paper manually deriving gradients and Jacobians and so on. And this process can be extremely error prone and leads to just nasty expressions that almost anybody double checks, or almost nobody double checks. Very few people do. So automatic differentiation is the solution. And if you think this comes at a performance cost, well, think again, because we actually ran quite a few benchmarks and compared to a whole bunch of popular topology optimization codes online for 2D and 3D problems. And as you can see here, most of the time, we're able to outperform all the other packages. Perhaps the only one package that was able to match the performance of TopOpt.jl for the most part was the Z Fergus's TopOpt package at the bottom left. But almost all the other ones actually were often significantly outperformed by TopOpt.jl. And this is basically, I guess, a testimony to TopOpt.jl as much as it is a testimony to the Julia programming language and its ability to generate efficient code. So if you're interested in all these optimization problems or the scripts, they're all available in TopOpt.jl underscore WCSMO-21 under my colleague's Yi Jiang's GitHub page. So you can find more details about all the settings, and we made sure we try to be as fair as possible in all these comparisons using all the same parameters and tolerances and everything. If you're interested in knowing more or seeing the details, then please visit this repository and open issues there. And we're more than happy to incorporate any changes if you think something unfair was being done. So yeah, and with that, I will hand over the virtual mic to my colleague, Yi Jiang, and he will take it from here, present some demos to you, and conclude the presentation. And I'll be there for questions after the talk. Thank you.
Thank you, Mohammed. Welcome to the demo session for TopOpt.jl. Today, I will walk you through a few live demos to show you the latest features of TopOpt.jl. We focus on SIMP-related algorithm today, but we also support other popular algorithms. So please take a look at the documentation of the package. Today, we will walk you through a few examples on 2D or 3D continuum domain, as well as a 2D and 3D example on truss domain. The examples involves popular compliance or volume constraint minimization problems, as well as one particular example on a volume minimization that's constrained on both stress and compliance. So for the time limit in the following video demo session, we will accelerate the video.
So the first step into the demo is to download the scripts. So please, you can find all the demos and benchmarks distributed with this presentation in this GitHub repo. One way to download it is to either git clone it by using this link, or you can directly download the zip and unzip locally. So next, step 2, we'll have to download Julia. So let's download Julia. Search for download Julia, and we choose the right operating system. In my case, it's Windows, and I will just download the installer. And I click open file. It will open the installer for Julia language, and I will just choose the default options of the installer. This will install the language itself, the compiler, and the interactive terminal, all the stuff that's associated with the language itself. I can click run Julia, and it will pop out a terminal window, and this is the interactive terminal window, REPL window for Julia. I will just copy the path here, and I type in semicolon. We'll enter the shell mode. We can cd. And I can just cd into the right path, so we can run the demo. Please type in the right square bracket to enter the package management mode, and then type in activate dot, which will try to change from the base environment into the demos environment. So this action will try to look for a file named project.toml. This file in particular document all the required packages to run this demo session. So after that, we can just type instantiate, and this will ask the package manager to look at all the required packages and fetch them from the crowd and install it locally and compile them. So this process will take 5 or 6 minutes, and we can reconvene after this is finished. Okay, now that all the packages are successfully pre-compiled, and now we can finally start running our tutorial. And here you can see here we prepared 2 folders. One is Continuum, the other is trusses, and each one of them contains several scripts. .jl is the Julia scripts name, and if you open the first one, you can see here is the Continuum compliance demo 1, and all of the script is very short. Let's run it first, and then I will walk through each what does it mean by each line. And so for Julia, for the first time you run it, it will trigger some compilation, so it will take some time, especially for the visualization part of our package. So while we're waiting for the running, let's work through what does every line mean. So here we start by importing or using, in Julia's terminology, out of the required packages. And in the first few lines, we specify all the material properties, the filter radius, the density, the minimum density, and the problem size. So here we're using a half MBP 2D example. So this altogether have 1,200 cells or little cubes in the ground mesh domain. And with the volume fraction and the penalty and the initial design, with the gas is the flow practice using the volume fraction to initialize the design. And here we construct the problem. So here we have several pre-constructed domains. For example, half MBB, point loaded cantilever, and other classic benchmarking domains already shipped with TopOpt.jl. But later, I will show you how do you define your own domain. Right after you define the problem, you can construct the FEA solver. So here we're using the direct solver to solve the linear elasticity to get the displacement. And then we construct the density filter. Also, we construct the compliance function right here. And then we built two Julia functions. One is to specify the objective and also the constraint, the other for the constraint for the optimization. And for the objective, we're trying to minimize the compliance. You can see here, we take a design variable and then apply the filter and pass it into the compliance function that we just defined here. And for the constraint, we're trying to get the volume fraction and then trying to have it put an upper bound on it, right? And here in TopOpt.jl, we use non-convex.jl, the other Julia package, as the optimizer. So here we're trying to build a non-convex.jl model. We add all the variables into the model and then add the constraint right here. So here, just pass the Julia function that we just defined for constraint into the model, and then we specify the convergence criteria for MMA, the maximum iteration, and the KKT and the delta X and delta F tolerance. And here we set the penalty, and then we just passing the model, and specify the optimizer MMA 87, and run the optimization. And after the optimizer is done, we can look at the objective, the constraint. Since that the optimizer has already finished, but notice that in this talk we will edit out a lot of the runtime to save some time. And if we go back to Julia, and you can see here the optimizer finished within 53 seconds, and this is the results as expected. This is the similar pattern from MBB. And notice that we are sliding support. We put a roller support here, and the load is actually loaded right here. And those sliders are just used for interactive visualization. And also we have support for interactively visualize the deformation. And this is the deformation under this point load for the optimized structure. You can see, as you can see, it's kind of sliding to the right hand side. Move on to the second demo. If you open the second script, continuous compliance 2. So the entire structure of the script is almost the same as the first one, except that we change from half MBB to point load cantilever. And also there's a critical change. We changed the objective and the constraint. So before, we're trying to minimize the compliance and trying to put an upper bound on the volume fraction. And here we're trying to swap them. So we're trying to minimize the volume, and we're trying to put an upper bound on the compliance. All right. So let's run the demo. Okay, now after a few seconds, optimizer finish, point load cantilever, you trying to minimize the volume and also put a bound on the compliance, and the results is like this. And again, we can visualize the deformation. Third demo I want to do for the compliance domain is was trying to do stress constraint optimization. So here we're still doing the point load cantilever. That's trying to minimize the volume, but add an additional constraint. We're trying to put a threshold on the micro von Mises stress. So here we add another function definition in the line 23. We define a stress function, and then so basically the stress function takes the design variable x, the design vector x, and then return the stress value for each single cell. And here we're trying to use a L20 norm to approximate the maximum function for the micro stress, and then put a stress threshold to bound it. So we basically just add this constraint to the non-convex model, and then we're done. So notice that we don't really have to do much in terms of to worry about all the gradient and hashing and stuff. TopOpt.jl take charge of that for you. So this is very easy actually to try out different constraints and different formulation with TopOpt.jl. So let's try to run it. Stress. Okay, now it's done. So we can see here that the design is changed a little bit. And specifically, if you look at the objective compared to the last round where we didn't add the stress constraint, we can see the total volume is a little bit higher. But as you can see, the maximum stress before it was 2, but after we add the constraint, we're trying to bound it to below 1. And then this constraint definitely working because we can see that the maximum stress is below 0.9. So the last demo that I want to show you for the Continuum is actually in using Jupyter Notebook. Let's try to type in using iJulia, and type in detached, true, and dear Continuum, and then let's open the Jupyter Notebook. And then so basically here compared to a script, we can actually run those things in cell by cell, so that we can easily keep track of the intermediate computer result. So we press Shift Enter, first load the packages, and then we, as before, we specify all the material property, and then here I'm trying to show you a script that define a new problem. I don't have the time to go into detail, but basically you just need to define a new struct, and then kind of define a function to specify where things are loaded and how the ground mesh is constructed. We have more detailed tutorial in the TopOpt.jl documentation. So the only difference here, just like a small demo, I'm just trying to reuse the point load cantilever example, but the load now instead of point loaded at one phase, it's kind of evenly distributed along. Here, after we define it, we can kind of construct the problem, and then as before, we construct the FEA solver. And the way we call the solver as a standalone thing is after we construct a solver, we can just like call it as a function to trigger the matrix assembly, and also within that it will also solve the linear system, and then after that it will try to return the u value here. And also notice that it's different to before. This is a 3D continuum example compared to instead of 2D. So here u0 you can see it's a vector for specifying all the displacement of the nodes in the domain, and then we can kind of call the visualizer to visualize the deformation. Notice that we're using the ground mesh here, so the domain itself will be quite dense. So you can see here, it's the ground domain because the deformation exaggeration factor is too high, obviously, and you can see here, it's showing the linear elasticity deformation. So to move on, everything else, the script is exactly the same for 2D and 3D, except for the problem definition. So here, you define the density filter, the stress function, the compliance, and define the objectives and constraint, and then run the optimization. So let's next move on to truss example. So here we provide you guys 4 examples in total. So there are 2D trusses and 3D trusses. For each 2D and 3D, we include one that minimize compliance subject to volume fraction constraint, but also minimize volume and subject to compliance upper bound constraint. It's the same as before. 2D one, for example, this is the final optimal results. For trying to minimize the compliance subject to a volume fraction constraint. Notice that this is definitely not a stable design if you consider a Buckle constraint. So we're working on Buckle constraint truss topology optimization. Also, take a look at how the ground mesh look like. So we can do so by typing fig equals to visualize problem. So you can see this is the ground mesh. We have another pair of example for 3D. I don't have time to go into detail here, but let's quickly just look at the result done, and this is the results. So the ground mesh is similar to the 2D example, except for it's kind of like cross-brace domain in 3D. All right. So with that, I will wrap up the demo session, and I will try to conclude the talk.
2 years ago, TopOpt.jl was first presented at WCSMO 2019 in Beijing. At that time, the package is still in its premature stage, where each new function has to be defined explicitly with a lot of template code. There were a lot of code repetition as well as interleaveness between modules within the package. After 2 years of hard work, we finally achieved to a state that we only have to define fewer special physics-based function, and we also allow them to be combined with regular Julia function easily, thanks to the excellent AD support from Julia language. We also achieve a better module separation between the optimization algorithm and other function definitions. And due to this separation, we allow users to easily experiment with different optimization algorithms without a lot of headaches and repetitive work. So moving forward, we want to further increase the modularity of the package. We also want to include more general FEA support so that we can use other FEA package within the Julia ecosystem. We want to work on massive parallelism and GPU acceleration. And also, we want to provide implementation to reproduce the recent advancement within the field of topology optimization, including stochastic robustness and reliability-based topology optimization, as well as level set method formulation. We are open to ideas, contributions, and all type of discussion at the GitHub repo here. So please give us a star and feel free to fork the demos and play with them and give us some feedback. We believe in the transparency and the commercial friendly nature of TopOpt.jl can be very beneficial to increase the impact and practicality of our beloved field of topology optimization. So please join us to build the next generation software for topology optimization. Thank you.